Hey, in this tutorial we're looking at section 6.5, which is about dynamics with connected particles. So two or more particles need to be isolated and resolved separately. Okay, and we've got to do that in the direction of motion, equate the resultant force to ma. Okay, so we can jump straight into some worked examples here. So we'll look at worked example 18. So we've got two boxes of mass 5 kilograms and 10 kilograms are connected by a string and lie on a smooth horizontal surface. So we've got 5 kilos, we've got 10 kilograms at the moment, okay, and then we've got a string between them, okay, and there's going to be tension force going in both ways in our string. A force of 30 newtons acts on the 10 kilogram box at an angle of 30 degrees. Okay, so we know that's 30 newtons and that's at 30 degrees. Okay, find the acceleration of the system and the tension in the string connecting the boxes. Okay, so we also have then our weight force down here of 5G, and we're going to have our normal force here as well, N1. We're going to have our 10G down here and our second normal force. So we've got our full diagram there. Okay. Okay, so we need to resolve horizontally around the 10 kilogram box. Okay, so we know with our force here, okay, so horizontally, okay, and our 10 kg box. Okay, so we're going to have our 30 cos of 30. Okay, minus t, okay, is going to equal our 10 A. Okay, so we don't need to worry about resolving vertically at all. Okay, it's just horizontally. Okay, and then we need to look at our resolving horizontally around our 5 kilogram box. So that means we're going to have T equaling 5A. Okay, to find acceleration we need to eliminate the tension in the string. Okay, so what we're going to do is sub this T equals 5A into here, so that we've got 30 cos of 30 minus 5A equaling our 10A. Okay, so cos of 30, well that's 30 times cos of 30, which is root 3 on 2. Okay, minus, that'll equal our 15A. Okay, so A is going to equal root 3 meters per second squared. Okay, so we've looked at each one separately. Okay, so what we need to do is just up here with our 10A, okay, so just to clarify where that came from, okay, we need to equate our resultant force to MA. Okay, so this is our resultant horizontal component. We need to result that to MA. Okay, so our mass of 10 times our acceleration. Okay, and so for this one, okay, the only force we had was T, okay, and that's going to equal MA again, which is 5A. Okay, so that's where our 10A and our 5A came from. So, and we need to look at particles connected by smooth pulleys. So the tension in the string is unchanged when it passes over the pulley. Okay, and that's the main thing that we need to worry about here. Okay, so when we look at worked example 19, so we have a block of mass 3 kilograms rests on a smooth table 2 meters from the edge. Okay, it is connected by a light, inextensible string that passes over a smooth pulley at the edge of the table to a second block of mass 2 kilograms hanging vertically. Okay, initially the 2 kilogram block is 1.5 meters above the ground. Find the time taken for the 2 kilogram block to hit the ground after the system is released from rest. Okay, so what we're saying is we've got something like this where we have a box that is 3 kilograms. So we have a 3G force acting on it. We also have a normal force. Okay, we have a pulley here. Okay, and we have a string that comes over it. Okay, to connect to another mass of 2 kilograms. Okay, so that's going to have a 2G force acting. Okay, and that's initially at a height of 1.5 meters. Okay, a 3 kilogram one is 2 meters from the edge. It doesn't really matter because this box is going to hit the ground before that one gets to the pulley. Okay, so we've got, and we also of course have our tension forces acting here. Okay, so we need to look at the isolating the particles and consider the motion of the particle hanging vertically. So the 2 kilogram block moves vertically downwards with an acceleration of a meters per second, because we don't know what the acceleration is yet. Okay, but we know that we've got a 2G force going down. Okay, and we've got our tension force in there. Okay, and that's going to be equal to our MA. Now our MA is 2 for our mass times our acceleration, which we don't know. I call that equation 1. Okay, the 3 kilogram block moves horizontally along the smooth table with an acceleration of a meters per second as well. So that's going to be our tension force. Okay, that's the only force we've got acting on our block up here is our tension force. So that's going to equal to MA, and our mass is 3, so it'll be equal to 3A. That's equation 2. Okay, so we're finding our forces and equaling it to MA. Finding our forces, equaling it to MA. Okay, so we need to substitute T equals 3A into here. So we've got 2G, take 3A equals 2A. Okay, so that means then that we can say, well, 5A equals 2G. So A is going to equal 2G on 5. Okay, so A, they've left it in there at the moment as 2G on 5, so we'll leave that at the moment. So we wanted to find the time taken for the 2 kilogram block to hit the ground. Okay, so what we're looking for is T. That's what we want to know. Okay, we know initially our velocity was 0. Okay, we know the distance that it goes will be 1.5 meters. Okay, and we know our acceleration is 2G on 5. Okay, and we don't know our final velocity. Okay, so we're going to need to look at using one of our 5 equations of constant acceleration. Okay, when we have a look at which one doesn't include V, then we see that we get S equals ut plus a half at squared. Okay, so we know our distance is 1.5, or we can say 3 on 2, because, well, 0 times t is going to be 0, okay, plus a half times our 2g on 5 times t squared. Okay, so we say our 3 on 2 equals our 2g on 10 t squared. Okay, so when we rearrange that, okay, we find that we get t squared equals 15 on 2g. Okay, when we rearrange that, okay, so we know t is going to equal the square root of 15 on 2g. Okay, we know g is our 9.8, so we go 15 on 2 times 9.8, okay, which we find t equals 0.87 seconds. Okay. Now, we'd be looking at this usually and going, well, hang on, what? Straight away it just goes bang straight down. Okay, our real life experience would probably say that it may not move at all. Okay, but that's because in real life we have our frictional forces in here as well that would probably actually stop this from pulling that across. Okay, in these situations though, when ignoring frictional forces so that we don't need to worry about that. Okay, so pretty much we're doing the same thing. We're isolating each particle, looking at the forces that we need to worry about, setting it equal to MA, rearranging and to find our A. Okay, and this one we just need to do a little bit more work because we need to find our time as well. So we'll keep moving. We're going to have a look at worked example 20. So I've got two particles of mass 3 kilograms and 2 kilograms are both hanging vertically and are connected by a light inextensible string which passes over a small pulley. Okay, so what we're saying, initially the 3 kilogram block is 1.5 meters above the ground. Find the time taken for the 3 kilogram block to hit the ground once the system is released. Okay, so we're saying that we've got a pulley, okay, and then we've got, let's say on this side, our 2 kilogram mass. On this side we're going to have our 3 kilogram mass. Okay, so we know that we've got a tension force this way, we've got tension force this way. We know that we're going to accelerate this way. Okay, this has a force down of 2g. This has a force down of 3g. Okay, this way the acceleration is going to be down. Okay, and we know that initially this was at a height of 1.5 meters. Okay, so we need to have a look at our forces acting on our 3 kilogram object. So we know that we've got 3g take t, so that's our resultant force, and that's got to be equal to our mass times our acceleration. Our mass is 3, so we say 3 times a. Okay, if we look at the 2 kilogram mass, then we can see that we have this time t take 2g, okay, equaling 2a. Now we need to change our direction because of the direction that we're saying our acceleration is going. So this time we're saying, well, acceleration is going this way, so t is in the positive direction and our 2g is in the negative direction, so that's why we're going t take g. Okay, and that's our second equation. Okay, so what we can do is we can add our two equations together. Okay, and we find when we do that we get g equals 5a. So if we add those two equations together, okay, so a is going to equal g on 5. Okay, then we want our time, so we go through and go, well, we want our time. Okay, we know initially our velocity was 0. Again, we know our displacement is 1.5. Okay, and we know our a is equal to g on 5, and we don't know our velocity, our final velocity. Okay, so we go through and go, well, which formula can we use that doesn't have our velocity? Okay, well, again, we can use our s equals ut plus a half at squared. So say our 3 on 2 equals our 0 plus a half times our g on 5 times our t squared. Okay, so our 3 on 2 is going to equal g on 10 t squared. Okay, that means that our t squared is going to equal 15 on g when we rearrange. Okay, which means t is going to equal the square root of 15 on g. So t will equal the square root of 15 on 9.8. So t will equal 1.24 seconds. Okay, so again, not a horrible worked example. Okay, so I've got one more worked example to do. Okay, and this one does have a fair bit to it. Okay, so we're talking about connected vehicles. Okay, in worked example 21, so we're going, a car of mass 1,400 kilograms is pulling a caravan of mass 2,850 kilograms up an incline plane of a slope of 1 in 4. The resistance to the motion of the car and the caravan are both 1/4 of their weight forces. Find the tension in the tow bar and the attractive force exerted by the engine of the car moves up the incline plane with an acceleration of 1 meters per second. Okay, so we need to set everything up here. So saying we've got some angle theta, we've got our caravan, okay, and then we've also got our car. Okay, so we're going to have tension forces in here. Okay, we're going to have our mass, which is going to be our, well, we know the mass of the caravan is 2,850 g. Okay, the car is going to be 1400 G. Okay, we've got resistive forces here. Okay, we've got, we'll call it R2 because we also have resistive forces here of R2, sorry, of R1. Okay, we've got a driving force up the hill. Okay, and then we've got normal forces acting here and the normal force acting there. Okay, so there's a little bit going on here. Okay, so we need to isolate the particles and resolve around each independently. So resolving upward parallel to the slope around the car. So for around our car, so saying that way for the car, then we've got our driving force. Okay, then we've got to take away our resistive forces, our R1. Okay, but then we also have to take away our tension force that's acting down as well. Okay, and we've got to take away the part of the weight force that's acting down, which is going to be our M1 G sine theta, or our 1400 G sine of theta. And we know that's going to equal our mass times our acceleration, okay, which is our M1, which is our 1400 A. Okay, now if we do the same thing for our caravan, so we're going up the hill for the caravan now. Okay, well, we've got our tension force acting up. Okay, then we've got our resistive forces acting down. Okay, then we've also got our mass of our car going down, which is going to be our 2850 G sine of our angle, equaling our mass, which is 2850 times our acceleration. Okay, so the resistive forces are 1/4 of our weight forces. So R1, okay, is our weight force, which is 1400 G on 4. Now R2 is going to be 2850 G on 4. Okay, so we can sub these in to our other equations, into our second equation, which is our equation here. Okay, so we can say then that we've got our T equals our R2 plus our 2850 G sine of theta plus our 2850 A. Okay, we know our R2 is 2850 G on 4. Okay, now we know our gradient of our hill was also 1 in 4, so we know then that sine of our angle is 1 on 4. Okay, so then we can say, well, we've also got 2850 G on 4. Okay, we know our acceleration in our question was 1 meter per second up the hill, so we can also say that we've got 2850 as well. Okay, and when we work that out, we get our tension force to be 16,815 newtons. Okay, or if you like, 16.815 kilonewtons. Okay, so we're getting there. Okay, so we need to substitute known values into 1 now. So we're trying to find our F. So we're trying to find our F here. So we're going to say, well, F is equal to our R1 plus our T plus our 1400 G sine of theta, okay, plus our 1400 A. Okay, we know that R1 is 1400 G on 4. We now know our tension force is 16,815 plus our 1400 G. Now we also know our sine again is on is 1 on 4, so we can say that is 1400 G on 4, plus our 1400. We know A is 1, so we'll just leave it like that. Okay. We know our G is 9.8, so when we sub our G in and solve this for F, we find that we have a driving force of 25,075 newtons, which is 25.075 kilonewtons. Okay, they do have a little bit of an alternative method at the end of that, but I don't think we'll worry about looking at that now. Okay, so that's all there is for this section. So generally speaking, they're not horrible, these ones. Okay, you just need to use your noggin a little bit and you should be fine. Just remember to isolate your particles separately. Okay, resolve the forces in the direction you need. Okay, and equate them to MA. Okay.